It's a particular polynomial, and cube is also polynomial. That's why quadratic is the specific polynomial 2 in the exponent. But okay, what is this? This is the most interesting one to talk about. So let's keep with the ice cream analogy, right? Let's say that there were 100 flavors of ice cream, right? So there are 100 ice cream, and you try them all, right? Every single person here has their 100 favorite flavors, right? And you came to the office today, you came to school today, whatever this is, and you wanted to give all of your classmates a taste of all of your favorite flavors. You have a lot of favorite flavors, 100 favorite flavors. So you have to give all of your classmates a flavor. How many scoops are you eating? Right? So let's say you have 100 classmates. Okay? Obviously that's not the right number, but it's a nice round number, decimal. You have 100 classmates, and you personally are going to give 100 flavors to each of them. Right? How many scoops are you? 10,000. That's a big number, right? Why is that number so big? It's because for each person, you're going to do 100 flavors, right? So if you add one person to that, how many scoops are you eating? Is it one more scoop? No, it's actually 100 more scoops, right? If you add one flavor to that, right, instead of 100 flavors, 101 flavors, how many more scoops are you eating? It's also 100 more, it's on the other side, right? So that would be n times m, where n is the number of scoops, and m is the number of students, right? If I increase one, you multiply it by the other. So that's a quadratic one, except the inputs are at different values. So if we want one that's n squared, let's maybe use an example of that, I can use that example myself actually. Let's talk about shaking hands, right? If when you come to class in the morning, the first day of class, pursuit is like, hey, we're gonna need to introduce you to everybody, right? You're gonna shake every one of your student peers' hands, and you're gonna say, hi, my name's Ben. You're gonna introduce yourself. Don't say my Ben, say your name, I'll say my name. Right, and you shake your hand, so shake your hand, shake your hand, shake your hand, shake your hand, right, shake yours. How many hands did I shake? Let's say there are 100 students. So I shook 100 hands, right? How many hands were shooken overall that day? 1,000. Is it 1,000? No. Sounds wrong. It's not exactly 10,000, but it's close, right? It's close to 10,000 because I shake 100 hands, and then how many hands do you shake? 100. You shake 100, but one of those is with me. With you, so. So you shake 99 more hands, right? I shake 100, including you, and then you shake 99 plus the one that we already counted, and then you shake how many? You shake another 100, right? But how many of those have we already counted? 2 of them, right? She already shook my hand, and she already took her hand, right? So that's 98 new handshakes. Plus 97, plus 96, plus 95, plus 94, all the way down to the last student who shakes 1 new hand, right? Actually, the last student shakes 0. Right? Well, it's not that sad because they've ended up shaking 100 hands. They've just been on the other end. They're never the initiator. They're just always the receivers. Some people like readers. So anyway, so that number, 100 plus 99 plus 98 plus 97, is basically 100 times 100 divided by 2. I can prove it to you. Just trust me on it. I don't want to spend too much time on the proof of that. There's a story about Gauss who's sitting in the back of the class. I love to tell it. In high school, it blew my mind, and I'm so happy. I'll teach you maybe during the break or something. But just trust me that when you add a number plus 1 minus plus 1 minus plus 1 minus all the way down to 1, it's basically that number squared divided by 2. Right? So it's 100 times 100 divided by 2, which is like 50,000, right? So 50,000 hands are shooken that day. If I add one new student to the class, instead of 100 students, I have 101 students. How many more hands are shooken? It's 100 more handshakes, actually. If I add a 102nd student, it's 102 more handshakes. Right? Actually, no, it's more. Okay, it doesn't matter. I'm bad at math. That's the thing, is computers are good at math, and that's why I'm a good scientist. I didn't do that well in college, but anyway, whatever. The point is that when you have 100 people all shaking each other's hands, you get 100 times 100 handshakes, right? So that is not linear. When I add a new handshake, it's not like one more handshake. Right? When I add a person, it's not one more handshake. That person has to shake everybody else's hands, right? So it's 101 more handshakes for that first person. Right? Anyway, so that is called quadratic. That is n squared. That's what this thing means. A very computer sciencey example of this would be if you had an array of numbers and you wanted to be like, how many of these numbers are duplicated? And you did it in a really naive way. You said, okay, look at the first number and compare it to all the numbers after it. Is it the same? Right? Compare the first number to the second, third, fourth, fifth, sixth, seventh, eighth, etc. I did n comparisons, right? And I saw if it was the same or not. Then I look at the second number and I compare it to the number after it. And I do n minus 1 comparisons. Then I compare the third number to all the numbers after it. And I do n minus 2 comparisons. So that's an n squared algorithm. Have I blown your mind? Anybody? What questions do you have? This is it. This is the biggest thing that I've learned today. Everything that we do from now on is just a derivation on this question.
Are you considering all these options quadratic?
Sorry.
Are you considering all these things quadratic?
Yeah. We're talking about quadratic right now.
Okay, so this is not this O(n) squared.
No, O(n) squared is quadratic.
Yes, but it's also O(n) squared divided by 2.
Right, so we will learn that here. Maybe that's coming down a little bit later. I don't know where it explains it. But basically, we do not care about linear coefficients. And I don't know if you've ever heard that word coefficient before. If not, don't worry about it. I don't even know what it means. But basically, if something is n squared and something is 10n squared, right? Let's say like something is 10, like n squared over 2. You have an algorithm that's n squared over 2. I have an algorithm that's 10n squared. My algorithm is 20 times slower than yours, but we have the same big O. And this is a weird thing. And the reason why this is a weird thing is because it comes out of, this is actually worth explaining. It comes out of Moore's law, which is actually not true anymore, but it was true up until about 2017. From 1980 to 2017, every 18 months, the number of transistors on the CPUs doubled. And this was just true. And some dude in the 80s, before like CPUs were really even that popular anymore, maybe in the 70s, I don't remember when he said it, was like, you know what? We're going to double the number of transistors on a CPU every 18 months. And by God, he was funny. He was right for literally 35 years. Right? He was right, like crazy right, to a shocking degree that affected us all in a profound way. This law is why we have cell phones. This law is why we have like Wi-Fi. It's why we have laptops. It's why we have the internet. And the internet maybe is a stretch, but it's why we have so many devices on the internet. Right? It's why we have cheap microcontrollers. It's an unbelievably profound law. It's not really a law because it was an observation that happened to be true. Years, it's not even true anymore because we've gotten to the point now where we can't put transistors on a chip beyond like 14 nanometers. We'll get to 11 nanometers soon, but like the rate of compressing has gone down dramatically in the past 4 years. We've sort of hit some theoretical or some quantum mechanical limits on like how small these like transistors can be. Right? But up until then, up until like 3 years ago, it was true that computers just got faster. If you had a program, if I had a program that was 10n squared, you get a program that was n squared over 2, I'd be like, guess what? I'm just gonna buy a faster computer than you. Woo! And now I've got a faster computer, and that the fact that my program is 10 times slower than yours doesn't matter. Because in 3 years, every computer is gonna be 10 times faster. Right? It's gonna double in 18 months. In 3 years, it's gonna be 4 times, right? And then in 4 years, it'll be like, 7-ish times faster. Suddenly now my program is faster than your program on the faster program. And so that's why in Big O, we don't really care about the linear coefficient. We don't care about 10 times faster, 5 times faster. We care about the size of the input. Because what it means is that if my program is 10 times faster than yours, or your program is 10 times faster than mine, both of our programs are going to fall over if we give it 10 billion tweets. Even though yours is 20 times faster than mine, right? If mine takes 30 years to complete, and yours takes 1 year to complete, it's still too slow, right? And what you find with these exponents, right, is that if you have a program that is n squared versus a program that's n, very, very, very quickly with large inputs, the linear coefficient just drops away. And the number of like real-time seconds of like, how long does this program take with 10 billion tweets? It's like, well, your 20x program takes like a year. Mine takes 30 years. But Ariel wrote a program that's n log n. She wrote a program that's linear, right? Ours are exponential, right? Ours are quadratic. And Ariel's is linear. Well, hers, when you give it 10 billion, it's done in an hour, right? And that's like just a huge difference. It's like, obviously I want the hour one versus the year one. Does that make sense? And so when we think about this as a function of the input, the linear code is stronger.
Kind of want to go back to the whole bit squared.
Yeah.
And just times 6 plus. So when did you divide by 2? Divide by 2. When did you divide by 2? When you answer the question.
Oh, so basically you're talking about like the sum, like it's like this Boyd-Gauss sum of consecutive numbers. This is the story of Gauss. This is the one you want to hear. Okay. So I'm going to tell you the story. Okay, I wasn't going to say this, and I wanted to go fast, but whatever. It's so fun. I love the story so much. So basically, Gauss was in the back of the room, mouthing off. And she was like, "Shut up, boy, Gauss." And Gauss was like, "I'm bored. I don't care. I already know all this stuff. I'm smart. I don't even learn this." And the teacher was like, "We're trying to teach all the students all this great math, and why are you like mouthing off? I need to shut you up. I have an idea. Gauss, why don't you add all the numbers between 1 and a billion? That'll take you forever, right? Go do it." And Gauss is like, got the answer. And she's like, "What? How did you do it?" And the way that Gauss did it is he looked and he saw a pattern. He saw, hey, if I take the last number and the first number and add them together, what do I get? Let's say I'm doing 1 to 100. If I take the last number and the first number and add them together, what do I get? 101. If I take the second to last number, 99, and the second number, 2, and add them together, what do I get? 101. And add this 2 is 101. If I take the third to last number, 98, and I add the third number, 3, and add them together, what do I get? Yeah, that's weird, right? I'm always getting 101, right? And this is not that weird. If I draw it out like this, you can see like the black line connects, the blue line connects, so on and so forth forever. How many 101s are there in the sum between 1 and 100? No. How many 101s? How many
50.
lines are there?
50. Right.
50, right? Where to get that number 50? It's 100. Divided by 2. That's right.
Answer the question you love.
Yeah, and it's actually 101 divided by 2. Right? So it's n times n plus 1 over 2. That's what it is. So yeah, you'll see it down here. It'll say that should say that it's this. See, this is the answer. Right? It's n times, so this is interesting. So this is an example of a function. It's kind of hard to read right here. You can see that. N times n plus 1 over 2, that's Gauss's theorem. It says, I take the last number, I add 1 to it, and I multiply that by 50, the length over 2, right? But that is just n squared in big O. Because I don't care about the over 2, I don't care about the plus 1, don't care, right? That's just n times n, which is n squared. Yeah, we just don't care about that stuff.
I mean, it's always n.
Yeah, just because like we see the over 2 and we're like, hey, if I pass a billion in here, is over 2 gonna get bigger or smaller? It's gonna be the same. Don't care. If I pass a billion in here, is +1 gonna make it bigger or smaller? No, it's shit. N squared. Right? It's like the difference between a billion squared and a billion times a billion plus 1 divided by 2 is like whatever. Right? It's like that number, a billion squared, is 1 with 18 zeros, right? And then you divide by 2 and it's like, oh, it's 5 with 17 zeros. It's like, okay, those numbers are both crazy big. It doesn't matter, like the difference in them is very small relative to the absolute result. Does that make sense? It's like you gotta think about it like a drop in the ocean. It's like, oh hey, if I you know that like Confucian saying where it's like I take 1 piece of sand and I put it on a chessboard, and I put 2 pieces of sand on the second piece of the chessboard, then 4 pieces of sand on the next piece of the chessboard, then 8 pieces of sand on the next piece. How many pieces of sand I put in the last? You put more pieces of sand than there are stars in the universe. That's how quickly that grows, right? That's a crazy exponential growth curve that you're double it each time, right? It's 2 to the 64 is that number. So there's 64. There's 64 numbers on a chessboard, and it's this. It's like 1E19. So like, oh, can you see that rendered out? See if we can. Let's do it. Yeah. So look at that freaking big ass number, dude. And like, let's put commas in there to see how big it is. Right? That is the number of grains of sand that you would need to put on the last piece of the chessboard. And so the point is that, like, okay, now imagine if someone had like 1 billion grains of sand to give you, and they were like, add to that number, like, I don't care. Right? Doesn't matter. Because this is 1 billion is right here. So it would just be, that would be a 4. Be like, whatever, this number is not really that much bigger. Right? It's like you took a swimming pool sized amount of water and dumped it in the ocean. Okay, good for you. The ocean does not notice, right? Okay. Anyway, so that's why we don't care about like linear coefficients. Okay. Where were we? Let's keep moving. Okay, so big O of 1. This is an example of, given some array, this function returns the first element of the array. If the array is really long, it's going to take 10 milliseconds. If the array is really short, it's going to take 10 milliseconds. Doesn't matter how long the array is, it's constant time, right? Make sense? Linear time. There's a typo here that should be indented. I'll tell them this now. That's because it's tabs and spaces. Oh my god, can you believe it? Sweat up here. Okay, so this is going to print out every element in an array. You've got some array, got a lot of elements in there, loop through them, print them out, right? If you have a array of length 1, let's say it takes 10 milliseconds, well, array of length 10, it takes 10 times as long, array of length 50, it takes 50 times as long, array of length 1,000, it takes 1,000 times as long. That's about 10 seconds, right? 10 seconds is 1,000 times 10 milliseconds, okay? So cool. Let's do, oh yeah, so here are these like cool things. Wait, what am I saying here? This example, gives the size of our array, does increase how long it takes over to run. Going back to our days of algebra, we can make a math function that explains the relationship between length and the runtime. So yeah, so this is a cool question. If I were to write a function that took as an input the array length and returned the number of seconds it would take, what would that function look like? 10 times n. Exactly. 10 times n, right? And if I got a computer that was 10 times faster, instead of 10 milliseconds, it would take 1 millisecond. It would be 1 times n, right? But it's still linear time. So this thing is 10 times n, it's linear time. Okay, where did the 10 go? So here's it written down, but I've already talked about this. Big O cares about the big picture. That's why it's called Big O. It's not why it's called Big O, I'm going to tell you that. While it can be very relevant to our code to make something 10 times faster, and it is true, if you can make your code 10 times faster, definitely do it. But generally, your program isn't that, it isn't that important to make it 10 times faster. It's more important to make it go from linear to constant or from quadratic to linear. You're going to see a more valuable speed up when your inputs get large. And large inputs are usually the only inputs that matter. The small inputs, it's like computers are fast. Whatever. So the main reason for this is that the 10 millisecond figure is not part of our algorithm, right? It's like the fact that it takes 10 milliseconds to do this thing is an implementation detail. I could write a new programming language, right? Script that is much better than JavaScript at getting array elements. And now the same program written in script runs 10 times faster, but it's the same algorithm. We're not evaluating the programming language. We're not evaluating how fast your computer is. We're evaluating your algorithm, right? That's what this is about. Does that make sense? What questions do you have about that? No questions? It's all good? Okay. We did that, we did that. If we had a better computer, we'd take blah, 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 blah. Okay, here we go, quadratic. So you can generally tell something is quadratic when you see a nested for loop, although not always, right? So it's not like anything where you're like, oh, nested for loop, it's quadratic. Not necessarily. There are plenty of nested for loops that are not quadratic, but it's a good guess if you see a nested for loop that is quadratic. And you can see here what it does. It takes the array, and it loops through every element of the array. And for each element, right, this is like saying, for each student, then loop through all the other students and shake their hands, right? It's not like one student shakes their hands, done. It's like, no. One student shakes their hands, and then the next student gets up and shakes everyone's hand. And then the next student gets up and shakes everyone's hands. Does that make sense? Right? If everyone needs to shake everyone else's hands, it's not enough for one student to shake everyone's hands, right? That's what's going on here. We're just saying, for each student, then for each student again, print the back. So this is basically printing out all the different combinations of like let's say that we were doing a tournament or something, like a World Cup, right? The Women's World Cup just happened. Like it was like every possible World Cup team playing every other possible World Cup team, right? How many possible combinations of teams fighting each other could there be? N squared. Make sense? Question?
So is there a way for us to recognize this takes N squared?
By the way that it is. No. Yeah, I mean the way that you do it is like the way that I like to do it.
Generally speaking,
right. So I like to do it, I go line by line, and I say, okay, this is a function. Great, you can tell me anything. All right, this is a loop. This is a loop. How many times does loop evaluate? N times. How many times will this loop evaluate? Well, it will evaluate, this loop itself is a loop of size n, right? But it is inside a loop of size n, therefore it's n times n. So this line will go n times, there I just figured it out. And I just do it by, I write it, like I just do it in my head, but if I was writing it down, like I could do something like, okay. Read my like personal notes here, but I think it's this, I would be like, this is n, and this is also n inside n, therefore it's n times n. Right, and then if I had like a loop in here that was like 4 element of array, right, like this thing, but then it was like if element, you know, says element 3 or whatever, it's bigger so you can read it. It's element 3. If element 3 is equal to like, I don't know, let's say it's like mod 2 is equal to 0. Parentheses here, JavaScript. And return, right? Then it would be like, whoa, this returns if like the element is odd, right? Right? So now I'm like, okay, this thing runs n times. This thing is going to run n squared times, right? This is a loop that runs n times. This is a loop that will also run n times, so it's inside the loop runs n times, so it's n times n. And then this is a loop that runs n times, inside we run n squared times, so it's n cubed times, n times n times n. And then this is gonna run n cubed times, but the first time that it ever returns true, we're done, so we're out of here. So the runtime of this no longer is, it was n, then n squared, then n cubed, now it's actually constant time with respect to the distance between the, basically how many even elements do you have. So if you have no even elements, it's n cubed. If your first element is even, it's big O of 1, constant time. Right, so I just like figured it out by looking at it. I don't know, it's like, there's no like magic way. It is very much, like this is an example of a function where it's like worst case n cubed, best case constant. And that's not an unreasonable answer, right? You're probably going to learn about, maybe you already have, quicksort. Quicksort is the most common sorting algorithm to sort arrays of numbers. There are like really, really neat implementations that make it very, very fast. It is worst case n squared, best case n like. And that's like the answer for that thing. And it's like, it's a very, very common, popular, you will definitely get an interview where someone's going to ask you that question. Okay, anyway, and they'll ask you about performance and stuff. So yeah. All right, cool. So this one's complicated. We talked about it. Cool. Print out each pair of names. So for this input Agnes, I'm going to call someone that talked over there in the blue shirt in the corner. Hey, what's up? For this input Agnes, what will this function output?
Output Agnes.
It'll be player 1 Agnes, player 2 Agnes. Right? Is that right? Okay, cool. All right, now let's say I do Agnes Bart. What's the output now?
Output be Agnes, player 1 Agnes, player 2 Agnes. Player 1 Agnes, player 2 Bart.
Oh yeah.
And then player 1 Bart, player 2 Bart.
Should we one or should we a fourth one?
Bart Agnes, player 1 Bart.
Yeah, Bart Agnes, exactly. Agnes Bart, Bart Agnes Bart. You're close. Right, it's every possible combination in each slot, right? So, okay, cool. What about Agnes, Bart, and Carl? Let's try that one out. But you right here in the blue shirt. We'll stick there. What do you think this prints out? If I put Agnes, Bart, and Carl as the input to this function. Let's try.
When you give me player 1, I do the same thing as this one, but give you all the possible.
Let's do it. Let's rapid fire, rip them out. Let's
So
go.
I have like Agnes, Carl, Bart, Agnes, Bart, Carl, Bart. We already did Agnes, Carl, so Bart. So Bart.
Right. It's like, I mean,
Oh,
think about it the way the algorithm is going to do it. Right? The algorithm is going to start with Agnes and do everything with Agnes with player 1. So it's Agnes, Bart, Agnes, Carl. Then it's going to go to Bart and do everything with Bart. Bart, Agnes, Bart, Carl. Then it's going to go to Carl and do everything with Carl. Carl, Agnes, Carl, Bart, Carl. Is that correct? Got it. How many are there? You just count them. How many are there? There are 9, right? What is 3 squared? It works. Okay, I'm not going to make anyone do this really long one. No. Okay. So, check this out. So now if we look at this graph, it's really cool. If the array length is 1, right, we print 1 time, it takes 10 milliseconds. If the array length is 2, we print 4 times, it takes 40 milliseconds. The array length is 3, we print 9 times, 90 milliseconds. The array length is 4, we print 16 times, 160 milliseconds. Notice how we add just 1, right? And we go from 90 to 160, right? We just added one new thing. We're like, here, do all this stuff with these tweets. And it's like, oh, you know what? Croatia wants to join the World Cup. Okay, cool, get everything here. Suddenly now, a lot more possible combinations are happening, right? It's not just the difference between 3 and 4 is bigger than basically everything previously combined, right? So that is really big, right? It's changing very quickly, it's growing very quickly. That's one of the reasons why the linear coefficient doesn't matter, right? Because if we made this 10 times faster, sure, it'd be 1, 4, 9, 16. But we wouldn't have to add very many. We'd go up to like 6 or 7 before we're back up to 160, right? Right, it'd be like, yeah, whatever. It would be like 9 or something. 8 would put us up to like 512, right? 7 would put us up to 256. So all it would be is, would it be 2 to the 1, 2 to the 2? Yeah. Is 2 to the 5 is 32, 2 to the 6 is 64, 2 to the 7. So 2 to the 7 would put us like close to this now. So all we need to do is add 3 more and we'll be back up. There's 3 more, it's not that many. Okay, so it's 10n squared, it's n squared. Okay. So we can see that what's really interesting about this n squared is that with the same chart, which 4, it's 160 milliseconds. If we put in 1,000, it's 2.8 hours. Okay? I didn't make that shit up, right? That's just because we're like, what is this? It's just 10n squared, right? So let's do that. 10 times 1,000 squared, right? We'll set up like seconds in hours. Look at that. That's 2,700 hours. This is. No, it's nice. 10 times 1,000 squared, right? 1,000. Well, because it's milliseconds. That's why.
Milliseconds.
Milliseconds. The math checks out. Okay. So that's why it's like, hey, it doesn't matter that this thing is 10, right? Because if I want to do it with 1,000, it takes 2.7 hours. That's crazy, right? So it's like, well, if I made it 10 times faster, okay, sure. It would take like 10 times less, but then all I need to do is 1,005, right? And now suddenly I'm slow again. I'm back to 2, right? Because if I do, let's say it was like we were doing this thing, right? We did this, and I was like, okay, let's make it 10 times faster. Now it's only 0.27 hours, so let's do it in like minutes, right? Now it's only 16 minutes, and I want to just add 5. Wait. Yeah, 16 minutes. 5 is, I don't know, what's that, 50? What? What's that, 5? Let's see. Yeah, now, so like, we're basically, if we go to 2,000, let's say, then we're back up to an hour. So it's like, I made it 10 times faster, cool, but all I need to do is like, I went from 1,000 to 2,000, and which is like not that crazy. It's not a lot, but it's like, hey, I want to try 10,000. I want to try 100,000. I'm slowly cranking up my algorithm. We'll see that like we're back up to the same kind of number steps. This example didn't work out very well because it was pretty fast. Okay, so as the bang, what does that mean? Kind of typo. We'll talk about that. Okay, we'll put it all together. Let's just look at that. This is better. So we can see that we've got array length 1. We take 10 milliseconds at runtime 1, 10 milliseconds at runtime n, and 10 milliseconds at runtime n squared. But as we grow to a bigger input, constant stays the same, linear grows with linear, and exponential, quadratic grows crazy fast. That makes sense? So this is why this stuff really matters. Okay. So log of n is the really big and exciting one, and we're going to do that next, and then take a break. Yeah. Let's finish this big graph. Okay. So it's interesting that we're getting in the other runtimes because like we mentioned there's the 3 most popular, now like there's actually 4. This is the 4th most popular one. Log. Okay. This one is by far the hardest to understand. If you only understand one if you only understand the top three, linear, constant, linear, and quadratic, you're doing well. If you don't understand log, it's fine. Definitely do understand linear, constant, and quadratic. But if you can understand log, forget it. Okay. So what log means is it's the inverse of an exponent. So you know when I say like n squared, what I'm saying is n times n, right? It's like the handshake function. When I say n cubed, it's like n times n times n, or n to the fourth. It's like n times n times n times n, right? That's what that number means. When you see that number at the top, it means take the number below and multiply it by itself that many times, right? So what the log is, it's the opposite. It says, how many times do I have to raise 2 to the power of, like 2 to the power of what is equal to n? Does that make sense? So it's like, maybe like write this down. There it is. So I'm like 2 to the 5 or whatever is equal to 32, right? So it's like 2 to the what is equal to 1024. Does anybody know? 2 to the what is equal to 1024. Whoa. Close. Small, lower. Higher.
10.
Got them. 2 to the 10 is equal to 1024. When we talk about a megabyte, I don't know if you've ever seen, sometimes you see this, megabyte, like that. See how that I is like lowercase and then black or whatever? That actually means a millibyte, which is not 1,000 bytes. It's 1024 bytes. Okay? Anyway, whatever, that's neither here nor there. 2 to the what is equal to 1024? The answer is 10. So this is saying log of 1024 is equal to 10. Log of 2048 is equal to
20. 15.
Who said that? Are you right there? That was you with the cool Lakers hat? Good job, Lakers hat. Let's do log of 4096. 12, right? Because this is saying 2 to the power of 10. 2 to the power of 11 is just saying 2 to the power of 10 times 2, right? 2 to the power of 12 is just 2 to the power of 11 times 2, right? Just like n cubed, it's just n squared times n. You following? So that's what a log is. A log is 2 to the what? And logs actually can be base anything. You have log base 10, log base 8. There's all kinds of logs. When we say logs in computer science, we mean log base 2. If somebody is like, no, I want log base 10, call them a fucking name. Go back to math class, go back to college. You're not in math class here. We're computer programmers. We do log base 2. Crush it. No, I'm just telling you, that's what we mean when we say it. It's like when you say drive, you say I'm going to drive there. Do you assume that I'm going to drive a bus or a tractor? It's like, no, you're going to drive a car, right? And it's like, you can drive all kinds of things. You can drive your mother crazy, right? You can drive me up the wall, right? You can drive your company to the ground. If you say I'm going to drive to the office, we assume you're talking about driving the car, right? Or like I'm going to ride to to school or whatever. Like, are you going to ride the subway, right? Like we just assume we take language and we make assumptions about it. When we say log in computer programming, we mean log base 2, right? That's not to say that it's the default. That's just to say that like that's what we mean. Okay. So notice what's interesting about log is that this number here, 1024, that's the n, right? Log of n, right? I'll say like log of n, right? So you remember when I had like n squared, right? That's the next n squared. And I was like, well, sweet. When n is like 10, it's 100, right? When n is like 1,000, right? 1,000 times 1,000 is like freaking big, right? It's a million, right? So as I make n bigger, n squared gets really big, right? If I make n bigger in log, the log value doesn't get that much bigger. right? If I add 1,000 here, right? If I add 1,000 here, right? Let's say I was at log of 1,025, and I add 1,000 to n. It only went up by 1. That's so little, right? Then I add another 1,000. It didn't even go up by 1. I had to add 2,000 to go up by 1. In order for it to go up by 1 again, I have to add 4,000. Next time I'm gonna have to add 8,000. So in order to get it to go up by 1, I have to add more and more and more. Log is very, very good performance. If your program performs at log speeds, you're doing really well. What's better, linear time or log time? Log time, right? Because when I add 1,000 to linear time, how much longer does it take? 1,000. It's linear. For every one I add, linear costs 1 more, right? When I add 1 in log, though, it costs a lot less than 1 as it gets bigger. What's cool about log is as you get really big, it costs even less. That's why it's not the same as linear. It's not like linear divided by 2. Linear divided by 2 is like, no, it's smaller than linear. But I've added 1 to linear divided by 2, I get add a half. Right? If I have linear of 1,000,000, my input is 1,000,000 and add 1, I still add half. Right? But if I have log of 1,000,000 and add 1, I am adding a tiny fraction. If I have log of 1,000,000,000 and add 1, I'm adding the most infinitesimal, unbelievably, don't even know how big it is. Okay, so let's talk about an example of log. I want to use a real world example here. I want to use a big world example. It doesn't seem like Benstow went too deep into it, probably because he thought it was really hard, which it is hard. But let's think about it. Imagine if I have a room full of students, and I want to divide them into groups of 2, right? All the people that love cake, and all the people that love pie. Okay? And let's just pretend for a minute that I'm going to choose categories that, in general, on average, have close to 50-50 representation, right? So it's like, about half we love cake, with half we love pie. Divide you in half, right? I did one operation, now there's 2 groups of size n over 2 and n over 2, right? Then for each of those groups, I divide those in half of like, okay, people that like Macs and people that like Windows. Let's just pretend it's 50-50, right? So now I've got 4 groups, n over 2, n over 2, n over 2, or sorry, n over 4, n over 4, n over 4, n over 4, right? How many times do I have to divide in half until the groups are of size 1? How many times? What do you think, Mariah?
I forgot. I don't know. I got confused after Mac and Windows.
That was the last thing I said.
Yeah.
This is what I got.
My state is,
So you were
my current status is, over 4.
right, exactly. So we started with n students.
Yeah.
Then we divided into 2 groups of size n over 2 each, right? If we divide each of those into 2 groups, how big are each of those groups? Quarters, right? Quarters, right? Then we divide each of these quarters. We divide each quarter into half. How big is now each group? 8s, right? We divide each of those 8s into half. How big are they now? 16s. So that number on the bottom is growing really fast, right? It went from 2 to 4 to 8 to 16. What's the next number in that pattern? 32, right? So how many times do I need to divide by 2, right? Divide you in half until each group has 1 person in it or fewer. Log, right? I mean, that was a good guess because I was just using log. So that's what it means, right? It's the inverse of exponent, right? If I multiply something by 2 enough times, it gets really big. If I divide something by 2 enough times, it gets really small, right? How many times do I need to divide it by 2 until it's 1? It's the same as how many times I need to raise something by 2 to get to the original number. Right? They're the inverse of each other. Right? It's like, imagine if I had a class of 1 student and they, I don't know, they split and we led to 2. Each of those split and we led to 2. How many splits until I get the class, right? So like, okay? No? Is that helpful? Okay, that's what it is. We are going to look at a graph. Okay, so then there's a couple of interesting things here that we want to talk about really quick. Log of n, we talked about it, right? So a really good example of an algorithm that we use in programming is the binary search. I feel like I'm actually not going to tell you because it's going to blow your mind, and I don't want to blow your mind just yet. It's like blowing your mind enough for now. We'll come back to it later. So there exists algorithms that are called binary search. It's really good. N log n. N log n is how fast sorting is. So n log n is a very interesting length. It's longer than linear, but shorter than exponential. It's a lot shorter than exponential. Right? It's a lot shorter than quadratic. But it's a little bit longer than linear. It's like linear plus a little bit extra, right? And that little bit extra is kind of big at small numbers, but as the numbers get big, it really starts to perform better because, like we know, log of n doesn't grow very big, right? Log of 4,000 is just 12, right? So it's like if I've got a really big number, right? Like log of 1,000,000 is 20. Log of 1,000,000,000 is 30, right? So it's like, okay, sure, it's 30 times worse than linear, right? But it's really not that much worse. It's almost a linear coefficient. So n log n is a really good runtime. It means like, hey, we have to check every element, and for each element, we need to do some kind of divide in half for each element. And so I can give you an example of that, but it's going to blow your mind on one here. 2 to the n is absolute dog shit. Like, let's imagine 2 to like 100. Like, look at this number. Holy shit balls, this number's going to be. Let's do it over. We have a terminal. Yeah, that's some SQL output. It is. So what was it? It was 2 to, it's like 2 to the 10 is 1024, right? 2 to the 20, whoa, that's a pretty big number. 2 to the 30, holy shit, it's getting really big, right? Oh my god, wow, this number's huge. And like, oh my god, that number is bigger than the number of atoms in the galaxy. Right? It's like an absolutely enormous number. And that's just 100. Right? Remember how many handshakes it took to do, like, if everyone handshake each other, there were 100 students, it was like 100 squared divided by 2, it's like 10,000, it's like 50,000, 5,000. Squared divided by 2, 5,000, right? So like at 100, an n squared algorithm, n squared is not very good. Linear at 100 would be 100, right? Exponential at 100 would be 5,000. 2 to the n, right? They call this exponential. So quadratic at 100 was 5,000, but exponential at 100 was like in the quintillions, in the googolplex, right? It's in the like absurdly big, like the size of this. So if you have a program that runs like this, it cannot perform anything other than trivially small inputs. So we have functions like this. This is some of the complexities of some major technologies in the world rely on the fact that these algorithms are so shit. A good example is like blockchain, Bitcoin. It doesn't use specifically like exponential, but it uses algorithms that are so bad, there's no better way to do them. That incredibly bad performance is a feature of the algorithm. It means that it requires a lot of people to check your proof of work. Sorry. You don't know about the corner notes, folks. Factorial is even shittier than that. So 2 to the n is saying 2 times 2 times 2 times 2 times 2, however many 2's, n, right? N is 172's. This is saying, n factorial is saying 100 times 99 times 98 times 97 times 96 times 95. So it's basically, instead of 2's, 2 times 2 times 2, replace it with the number 1, 2, 3, 4, 5. So it's strictly bigger than 2 times 2 times 2, right? 2 times 2 times 2 5 times is definitely going to be smaller than 1 times 2 times 3 times 4 times 5. Right? 'Cause it's the same number of terms. One of them is smaller. Okay, good. But the rest of them are the same. The second one's 2. And all the other ones are bigger. So it's definitely bigger. So if you have a n factorial algorithm, you cannot possibly do it for very big inputs. A good example is print out every possible ordering of the students in this room.
Yeah.
Right? Like if I lined you up in a row, and I was like, okay, you're all lined up. This is one lineup order. If I swap just one of you, it's a different ordering. How many different orderings are there? There are a lot. There are actually n factorial. Insanely large number. Right? So that's an example of that. Here is a graph of that. So you can kind of see, it's interesting that it puts n squared in the terrible range. It's kind of not. It's kind of like, it's bad. Like I would probably put bad, like put n squared in the bad range. But anyway, these are the graphs of those functions. So you can kind of see that like log n is really good. Log n is barely linear. It grows, right? Or it's barely constant. It grows. Constant never grows. Constant's flat.
Oh, and this graph is just showing the speed. Okay.
Yeah, exactly. This is a graph showing you these things that we've been talking about this whole time. Which is like everything that we've been talking about, this speed, this complexity, is a function of the input. The bigger the input, the slower it is, right? So you can see here with a small input, they're all the same. Right? With a small input, they're all the same. They're all very fast. But as your input gets bigger, it's like now linear is really fast, it's like constant is really fast. Log n is pretty close. Linear is not far off. Right? And log n is like, well, pretty good too. N squared is like, well, it really starts to get big. 2 to the n is like, wow, it looks like a vertical line up. Where at some point when you add 1, it just gets massive. Each one you add is just like, doubling the size of it. And then n factorial is just insane. That's what it is. That's the graph. Let's take a break. Everybody get up and stretch. Everybody get up. Get up. Stand up, stand up, stand up, stretch. Stretch them out. Stretch them out. Move your legs. Exercise creates brain cells. I don't know. I don't exercise.
Last guy is like.
This graph, where it's like adding 1 makes it, like let's say adding 1 and adding, I like here, let's say this is like 5. Right? Adding 1 makes it 6 times bigger. Right? So it's like here's your value, what's 6 times bigger than that? It's probably 6 times taller, whatever it is. If you're at 100, you go to 600. Right? I got 600, now 7 times bigger. That's 4,200 square added 1. So it's basically a vertical line. Nothing can be perfectly vertical, but it's like the scale of the graph. I'm saying that, yeah, they use these lower algorithms for like prime factorization. Prime factorization is a problem that they don't have. How long you use the GPU. There's no solution that's even this fast. The fastest solution is this. It's so slow. That's one of the most important ways that like security is done.
But that's not to make the code. That's someone who's trying to make it. You're trying to make it. Breaking desktop size. But those days isn't.
No, basically what you do is you generate some high numbers manually. It's really easy to like calculate numbers. It's really hard to figure out what the kind of numbers would be to generate this values. So it's like there's an asymmetry to it. And that asymmetry says, oh, fuck yeah, yeah, exactly. So basically, it's like imagine if you can guess a number very quickly. But for me, to figure out what you can guess in your head is very slow. Does that make sense? It's not exactly like that, but that's a kind of, it's asymmetrical, right? Where it's like a hide and seek. It takes you 5 minutes to find a hiding place, it takes me an hour to find your hiding place.
If you can make the password, it was hard for them to make it operate.
Yeah, exactly. But it's specifically doing that. So like when I go to some website, so like see this website GitHub, see right here it says your connection is secure, certificate valid. So what that means is that the data that I'm sending to the website and back is encrypted. So that encryption basically says, hey, you are going to send me a number. That number corresponds to a secret number that you have. So you basically have 2 numbers, and you generate them using this like mapping thing. You basically say, hey, I'm going to generate this like prime factorization. I'm going to like generate 2 prime numbers. I'm going to do some math and then have it work. And I take one number and I give it to you. And then you take that number and you use it, and you take all the data that you want to send to me, and you take Chief's data, you raise it, you take your data, make a number, and raise it to the power of that number. It's really quick. The math, you create some giant number. You put that number on the internet, you're like, what is this number? It's gibberish. I have a secret mother company that I can use to take the numbers that you generate, the power of that, to take the law, and turn it back on the original. That's what encryption is. It's like putting it on board, and almost like locking and if someone were to attack, they would try to guess the numbers and take them. Really long time. It would take it's like to the end. That's the size of the connection. Bigger arrays, bigger numbers. So two to the 64 is a huge number to form that. Break the impression. Yeah, sure. I can give you some recognition on So, you want to learn about that? Go to read this through and say. So it explains here this like how it works. There's a lot of high numbers. I mean, the thing is that programming is that there's that right? You don't have to do that. It's like it's like you ever have a test in high school, it's like no calculators. Never in college, no calculators. It's a lot. Is everybody back? We're waiting for the Are we waiting anyone else? Is the person sitting there? Is that person sitting here? Okay, well, we can actually start with that as one, because what we're gonna do is I want everyone to do, I want everyone to look at this driving content section and talk amongst yourselves right now. What is the answer? Right, so now talk amongst yourselves, so you're really quiet. I want you to look at this one and work with your peers in your little table in your group and try and talk about like, what is the runtime of this function? And if you finish it, you go to the next one. Go. Has everybody gone to the next exam? You're still working on this one. We're going on to the next. Did anybody finish the second one or is it all? Okay, some people, so maybe 1 more minute and then we'll finish the second one. Some people are already on the second one. Already done.
They're on the second one.
Okay, come on, here's the ball, here's the ball. Let's bring it all back, let's bring it all back. Shh. Who wants to do the first one? Maybe Ariel.
First one, you can try to read it.
Just tell us what you thought, tell us, explain your thought process in your answer.
When we talked about this group, Ray, and we thought that it should be linear just because inside the function there's a for loop and it's a statement and it makes you go through every character and you have to return true or false. It's not returning the same thing every time. It's not looking for this one thing. It's not constant.
So it's linear with respect to what? It looks like there's two inputs here, right? String and target bar, what linear respect to what?
Yeah, you're going through each character element in the string.
Okay, so it's linear with respect to the number of.
You're not gonna stop just at one, if you're like, I'm just looking for an equals draft, like you're not gonna stop at draft. At the first draft, you just look to check the other parts of the string.
That's actually not true, though. You will stop in the first draft.
Oh, we'll stop, okay.
right? When you return means
I
stop.
still need linear, but then I'm not explaining,
Right.
I don't have to write reasoning.
Right. No, so you have the right reasoning, which is there's a for loop here, and it goes going to loop through all the characters in the string. So it's linear respective, the number of characters in the string, also known as the length of the string. Right? So I think the right answer would be it's linear respective length of the string in the worst case. And in the best case, it's constant time because it's possible that the first element of the string is target character. Or the first element of the string is target character will be like, loop through it. For the first one, look to see, oh, I found it. So average case, it's n over 2. Right? Because on average, the thing you're looking for is somewhere in there, and it's halfway there probably. And n over 2 is the same thing, it's n. Okay, so we might need to look at each of the characters inside n. N represents the length of the string. The more characters we have in our string, the longer it will take. Okay, let's talk about example 2. Who wants to do us example 2? Ladies have. Should we do bull's hat instead? Bull's hat is like, whoa, gosh, that's like bull's hat, up on. Fingers suck right now. They're on screen. Right? They didn't even make the playoffs. It's embarrassing. It's embarrassing. Sorry, ladies hat. Bulls are not legacy. I guys. Oh my god. Also, already bull's hat. Constant. It's constant? Why? What about the array? How many times are you gonna print it? I print it a million. You said n. It's okay, don't admit it. Okay, you can admit it. That's the wrong answer. Okay, now I'm not calling you just because you're wrong, which you are. But no, I mean that's how this question is written to trick you into saying it's linear, right? And because it prints a million times, like Wilson said. Million times. That feels like a lot. But if I pass in an array of size trillion, you only print a million times. If I pass in an array of size 100 trillion, you only print a million times, right? Over time, this very slow algorithm would be faster than this very fast one if I gave it a big enough input. So it's a question. This million is array.length. Would that be linear? What does the class think? No! Why did you say no?
Because it's still gonna be a constant output of many printings.
Not constant. No, if this was array.length,
Yeah.
then the longer the array, the more printing. The shorter the array, the less printing. Right? This number of million never changes, therefore constant, right? But if we made this array.length, which Striped Shirt was asking, most of you said correctly, but I want to just double check if those of you that didn't. That would make it linear, right? Because what matters here is, does this number change with respect to the input? This number doesn't, right? This number is always a million no matter what. If Donald Trump was impeached today, we can only hope, this number will still be a million, right? But if we change this to array.length, then now, okay, what is this number? This number is going to change. Longer arrays can be bigger, shorter arrays can be smaller. So it becomes linear. Following that? Not exactly. Okay, I'm confused about it. Give me a question.
Because the answer I got was that it was constant, but I figure even though it would be a rate down line, it wouldn't really matter. But when you say that, is it because I don't know how to really put it into words, but because you're going by the length of the array, the amount, I'm not sure like
You're using my words.
yeah, I'm not sure like how does the amount really make the difference with the constant.log to make it linear?
So basically, you agree that this one is going to print a million times, right?
Yeah.
We all agree it's going to print a million times. A million sounds like a big number. But if I pass in a length billion array,
Yeah.
what's bigger, a billion or a million? Billion's way bigger, right? And if I pass in a billion array in that first one, how many times is it going to print? Just a million. Just a measly million.
Okay.
right?
Yeah.
If I pass in a trillion array into that function, how many times can I print? Still a million. So that sounds like, what kind of time? Constant time, right? Constant time, because it's slow constant time,
Yeah.
but it's still constant with respect to the input,
Okay.
right?
Yeah.
Okay? And then this one down here, this is that change that, what was your name? Giselle was saying, she was like, oh, she was asking, well, if we change to this, would it become linear? And the answer is emphatically yes. It is absolutely linear. This is the quintessential linear program, right? Hey, I have some array, do something for every element. That's a very common linear program. That's the kind of thing that, like, when you do an interview, it will be assumed that you know this, and they're going to try and ask you harder stuff that will be built on top of this knowledge, right? And so it's like, this is the foundational knowledge that I'm trying to give you, so that later in the class we're going to learn more complicated stuff that will be on top of this. This is foundational, right? This thing right here. And so this is a trick. This is a trick to say, aha, it looks like foundational linear, actually constant. Good job. Okay, cool. All right, let's do one more together. Who wants to try this one out? Let's try something we have to call one over here. This cool shirt.
It's rare because we have an array function that's using an array and it's calling another array for different function. And it's going to run that over and over and it's going to find the number that it wants. And how long that takes to do will be determined.
Okay, that I think we said this right, but it's kind of confusing. Can you say it again and we go slow?
So we have example 3, which when it's run, it starts and in that loop we're going to be looking in another function that also has a
Okay, so slow down. Okay, that piece right there is big. How many times do we call this contains function?
well, as many times as we have in the array.
Okay, that's correct. Another way to say that is n times, right? The length of the array, n, right, is how long this loop is. So we are going to call contains n times. So if contains is constant time, then this function is linear times with n. Contains is n times, then this function is n squared. If contains is log n time, this function would be n log n. Right? Does that make sense? So this is like to your question earlier, it's like, how do I figure this shit out? So this is that process where it's like, oh sweet, this is a loop, it runs n times, right? Length of the array times. But what does it do? It calls the contains method. I don't know how big that is. So however big that is, however fast that is, it's gonna be that times n. This is the whole function. That makes sense? So now let's look at this function down here, right?
Right, so it's this particular function that's doing the same and running with the time.
So this is example 1, right? This is the exact same as
I'll do that one.
Yeah, it's the exact same, right? It's the find target element in array, right? And so this is exactly what Ariel was saying. This is the linear time function that best case constant time, average case number 2 linear time.
So now we have to take this and use it in another function.
Does everybody follow that? Any questions on that? This is the skill that we are now learning, right? Which is that you can see some program you've never seen before. You should be able to figure out the runtime of it by like piecing it together and multiplying the pieces together. Sometimes you add them, sometimes you multiply. When would you add together runtimes versus multiplying times?
Maybe if they're not like in like you see how this one puts in another function into the first one. Maybe if they're just set to run separately.
Exactly. Right? So if I had this loop here, let's say this one here, and I go this J. right? So this one here is, this is n squared, right? It's the quintessential n squared with respect to the length of the array. So it's like I loop over the array. For each element, I loop over the array again. And that's n squared. This is the shaking everyone's handshake. Everyone shakes everyone else's hand. But if I were to take this here, put it there after instead of inside, right? It's the same code, right? It's the same code. It's just instead of putting it inside, I put it after. This is no longer n times n. This is n plus n. N plus n is just 2n. 2n is just, I want more. N plus n is just 2n. 2n is just, oh my god. Come on, folks. I know it's late, but like, I need it. I need it, it's funny. Okay, so we're gonna try this one more time. I'm gonna let you talk amongst yourselves, so if you know the answer, tell your peers, so that you all sound smart. Okay, ready? This is not n squared, right? This is n plus n. It does n, and then it does n, right? It doesn't do it inside each other. So do n when it's done, then do n. That's 2n, and 2n is just n. 2n is just n, right? Because whatever, who cares? 10n is just n, right? Linear coefficients don't matter. Okay. Okay, cool. So we talked about, we've already actually talked about this a little bit, so spoilers. We talked about runtime, we talked about average case, right? So that's why when Ariel was saying, you know, hey, it's possible the first element is the draft, then we're return immediately, you know, in constant time. On average, though, the first element is not a draft. The element is somewhere in there, it's about halfway in there on so it's the end, that's the front, that's the middle. On average, it's the middle, that's number 2, that's the average case. Almost, when we say big O, we mean average case. That's what the big O means. So it's also useful to talk about best and worst case. It's really useful to talk about best and worst case, right? In the example 1 up here, the worst case is that you never find it. Right? The worst case is that you get to return false. Loop all the way to the end. No, you get to the end. So that's the worst case, right? Best case is that you find it immediately. The average case is that you find it somewhere in the middle. Right? Does that make sense? So the best case runtime is constant, the worst case runtime is n, and the average case is n over 2. Therefore, average case is n. Okay. So let's look at this function here, and it's a typo there. And whoa, there's major typos here. Let's fix these typos. It's not good. This is the one thing. Time here. Let's see. Zoom in case. Plus. Good, right? That's fine. What was the class last week?
Yes, it's great.
I thought I had a clone already. Maybe I don't. I was sworn that I did. I want to like hold on, we gotta fix this. This is not acceptable. Okay, while I'm fixing this though, while I'm fixing this, let's everybody look at this function. Do you not have this side up on your laptop? Get this up on your laptop. I want everyone to look at this and talk amongst yourselves like we did before, and answer what is the worst, what is the best, and explain it. I'll be right back. Okay, cool. Anybody want to share with the class what they did? Let's try something. Okay. A little bit. So we're talking about this best average and worst for this function. What do you think?
By evaluating each one.
Well, yeah, you're going to give us the best, you're going to give us the worst, and you're going to give us the average.
That's would be the second one, is is that number, 867 number.
Sure. Well, yeah, but the question is, what's the runtime, right? What's the big runtime? What's the best runtime? We don't know. If it were to be this result here, also this one's pretty good too. How long would this function take relative to the size of the input? If it happens to return here, how long would it take? How long is no time at all? And here you go. No, n is a significant amount of time. N is the array is like a million, n is a million. Constant, right? So the best case is constant. The best case is that the array is very short, it just returns, or that the array it has the first element as some random ass number, and then it returns me, right? If that's the case, then it's constant. Okay, sounds good. Best case constant. See, look at that, constant. Okay, what's the worst case? Neighbor with the little cake all around. Okay, tell us why. Well, she should help her. She's the one who's supposed to answer. You're supposed to bring it.
I mean, I'm just going on limb here just because if, let's say the first if statement isn't met, you have to run this entire code that's doing a function within a function, right?
Which function are you referring to?
The third one?
So you're talking about this if statement.
Yeah.
You're saying if for some wild reason, first element plus the second element is this weird number.
Yeah, then it's asking it to do.
Yeah, so there's no functions in the function. I don't know what it's
Sorry.
referring to. You're probably talking about loops. You're probably
Yeah.
saying loops. Okay.
Um,
So you're saying the worst case is if this happens.
yes.
Totally, that's correct. Right? If this is a very unlikely case. Right? It might happen. And if it does, how long is it with respect to the size of the input? It's 1.5. Yeah. N squared. Okay. Yep. Make sense? Question?
Why?
So this function, right? It could return here. If it returned here, it would have been constant times. It's like, did a thing and it returned. Doesn't matter how long this array is. Actually, it doesn't matter. The array is very short, it just returns. If the first element of the array is this number, it just returns. So the array could be a length of 1 trillion. And the first element could be 8,675,309. The array could be a length of a bajillion. And the first element could be 8,675,309. Doesn't matter how long the array is. If the first element is this, it just returns constant time. If the first two elements of the array add together to this random number, 24,601, then we evaluate this code. What does this code look like to you? It looks a lot like this code, doesn't it? Looks really similar, right? This code here. This code here. So this line right here, right? What does it mean? It's looping over an array, right? So how many times is it looping? You're not sure. It's saying 4 element array. If I'm like, for everyone in the class, I am going to clap my hands. How many times do I clap my hands? As many times as there are students in the class. So this loop is going to loop as many elements as there are in the array. And another word for that is array.length. Those are the same thing. Array.length is how many elements there are in the array. How many elements there are in there is the length of the array. It's all the same thing. So this loop is going to loop array length times. This loop in here, it's going to run like it's even going to be created. It's going to be like, hey, clap your hands for everyone in class. It's like I'm going to clap my hands once for everyone in class. I'm going to clap, 36 times, right? And then someone says like, clap once for everyone in class for however old you are. And I go, shit, I'm 33 years old, so I'm going to clap 36 times, and then I'm going to do that again. I'm going to do that again, and then again, and again, and again, and again, 33 times. 36 times 33, right? That makes sense? Where it's like, do 10 push-ups, and then like try to run the block. And then do 10 push-ups, and then run on the block. Do 10 push-ups, run on the block. And run on the block 10 times. How many push-ups did I do? 100, right? I did 10, then I ran on the block. And I did 10, I ran on the block. I ran on the block 10 times. I multiplied them together. So that's what's going on here. This is driving around the block, and this is doing push-ups. And notice how they're both the same length. So it's like loop over the array, so do 11. And for each time, what we should do is loop over the array again. So that's a multiplication, right? Question behind you.
You said a loop inside the loop.
Yeah, totally.
So it went from being constant in different paragraphs just because it's looping again.
Yeah, well, it went from being constant because these weird constant cases are just weird bullshit. So programs are complicated. This like weird looking thing, it's kind of a stupid function. It's actually kind of maybe the least stupid function that we've done all of it. Because the reality is that programs look like this. You know, they look crazy, okay? Like look at this one. Let's close these tabs so we have one really big tab. This is like a real world code, okay? So it's like, here's some function, fire, okay? And look, it's got a loop here, right? So this function's got a loop in it. It's got a bunch of if-else's. It's got some array indexing. This is a project I've seen Golang, but kind of recognize it, right? You've seen JavaScript, you've never seen Golang before, but hey, you're learning. Programming languages have a lot in common. You know, you'll notice there's no parentheses for whatever. It's the same thing. So there's a for loop here over allowed tags. There's a for loop here over triggers. There's a switch statement, which is just like an if statement. So what is the performance of this function? It's linear with respect to the allowed tags plus linear with respect to triggers. So it's n plus m, where n is the length of triggers and m is the length of allowed tags. So I mean, like this weird function that we're looking at is just like, actually the real world looks kind of like this. It's full of random amounts of bullshit because most programs aren't like nice, simple little things. Most programs are like, hey, I'm making an app that like tells you all the cool restaurants in your location. Well, like, might be a location with not that many restaurants. You might be a location with a lot of restaurants. You might have a low internet. You might have a small screen. You might have a big screen. It's all these like weird variables that can affect the way that your program behaves on the phone, on the computer. You know, the user might delete all their things. They might add a lot of tasks. They might, you know, imagine if you're making a to-do list. You can have different groups. One user might have one group with 1 million tasks. One group might have 1 million tasks with one each. Another group might have 10 groups with 10 tasks each. All of these things your program needs to support, right? And so this function is oddly enough saying, hey, if this weird condition is met, return. So there's a case that if this weird condition is met, it's constant time. This weird condition is met, do this. And this code right here is n squared. Question that I want to answer that other question.
Is n times n linear or whatever?
It's quadratic, usually, but it's like, you know, yeah, it's technically quadratic, but it's linear with respect to it's linear with respect to n. It's linear with respect to m. It's quadratic with respect to n. You know what I mean? And because like it could be that n is small and m is big, in which case it's linear. It could be that n is big and m is small, in which case it's linear. Because they're both big, in which case it's quadratic. And so it's quadratic with respect to the distribution around us. Exactly. But it's not wrong to just say, it's not that interesting to say quadratic, that's just in shorthand. What you would say is big O and n times n. In an interview, you want to say big O. If you say linear or quadratic, you sound smart, you're good. But if you want the right answer, if the interviewer is like, no, I want what it is with respect to all the inputs, they want big O number. They want you right or whiteboard, big O for n times n. Sometimes it's like big O of n log m, or big O of n squared log m, or yeah, well, plus isn't that interesting usually. You usually care about multiplication. If it's plus, it's like whichever one is bigger is the one that matters. You know what I mean? Because if it's like tweets and length of tweets, it's like, well, you could have billions of tweets, but the tweets will never be longer than 240 characters. Right, so it's like that one falls away, and you only care about the bigger one. Okay, anyway, does this answer your question? I feel like you're still a little bit confused.
I am, to be honest. I don't know that. I'm confused to you. I did have to kind of like with the running sample, letting it sink a little bit more. That's what I see more. Sounds like the one that we're now. But clarify that streaming, because you said that it went from a constant to a quadratic.
Right.
So that's a concept that we have to keep in mind, that it just starts with something that so, yeah.
Yeah, well, I think the key is that there's these return statements, right? Return statements are very powerful. Return statements say done. So if you see a return statement, then you know, well, there are cases where I'm just done, right? So in this case, I'm just done, and the amount of time it takes to evaluate this return statement is constant time. And the amount of time it takes to evaluate this return statement is n squared, because I have to do all this bullshit before I get there, right? And so it's like any program can have like branching paths, you know? Any interesting program will have branching paths. Okay, so the dude behind you was asking about an example of a function that's nested, but not quadratic. So here's an example of a nested that's not quadratic. This one's linear time. Right? Here's another one that's nested, not quadratic. This one's constant. Right? Here's another one that's nested but not quadratic. If it's like array of I mod array is yeah. So. Right? So this one is also not quadratic. Right? This one is saying as soon as array dot length reaches 100, right? Some multiple over maybe so forth. Just yeah, that is good. As soon as I find some element which is a multiple of 100, escape. This is worst case quadratic, but best case constant. Because if the first element is a multiple of 100, bang, we're good to go, right? Does that answer your question? So yeah, just because you see a nested for loop is not good enough. You need to look at what this value is here. You need to look at where the return values are. If there's a break, right? Like this right here, it's constant. This thing runs one time. It enters here, it does I, it immediately breaks. This code is unreachable code. Might as well delete. You know, and that's the kind of thing like in the real world, you don't really care about in an interview. They sometimes try to trick you with this kind of shit. So it's good to know. Interview is very like test like. Okay, we're out of time. So we should go home. There's a couple more examples. I would love it if you were to just go through them. You know? So yeah, these are the ones we've seen before. Best case worst case, we already talked about that one. Best case worst case. So a lot of these best case worst case we actually already talked about. And this is the really interesting thing. Probably won't pick up here. Yeah, do yourself a favor and review this material on your own time.
So, can I ask your attention for a second? So tomorrow we're going to have the professional. Sorry, I always feel we have class on Thursdays. Saturday we're going to be working on the professional skills workshop in the morning. In the afternoon we're going to do a review of all the stuff that we have learned so far. There's going to be a lab and it's going to be really hands-on reviewing what we've learned. As Ben said, please get through the content of the lesson remaining. So with that, also what we're going to be doing is when we're writing any piece of code, I'm going to be asking you, okay, let's look at the time complexity of this algorithm. So that this only comes with practice, and I hope that with that repetition, we start to get a real sense for this. Thank you, Ben, for the lesson.
Thank you.